time varying fields. So till now we have discussed electrostatics and magnetostatics, right? The electric and magnetic fields which are constant with respect to time. Okay. Now we are going to deal with time varying electric and magnetic fields. Okay. So what happens when there is a static electric field and a static magnetic field? Then they are independent of each other. Okay. Static electric and magnetic fields are independent of each other. Okay. Whereas time varying fields, they are interdependent, that is one will lead to the other. Okay. Time varying electric or magnetic fields are interdependent. So a time varying, if you take a time varying electric field, okay, this will involve a time varying magnetic field, and also vice versa. That means a time varying magnetic field is going to involve a time varying electric field. So you can summarize like if you take a static charge. Okay, so when we had static charges, what did we get? We got electrostatic fields. Okay, electric fields which are constant with respect to time. And when the charge was moving, we got a magnetic field. Okay, but when do we get a magnetostatic field? When the electron or the any moving charge, that is when it has a uniform velocity. Okay. So when the charges have uniform velocity, what will happen to the current? The current is going to be constant. Okay. So a constant current, or you can say a steady current, this will give rise to a magnetostatic field. Okay. So constant current means that the charges are moving with uniform velocity or constant velocity, right? So that is going to give rise to a magnetostatic field. Now we have time varying currents. Okay, so that means the electrons do not have uniform velocity anymore. Okay, so when there are time varying currents, then you are going to get what is called as an electromagnetic field. Okay, so that means both electric and magnetic fields are going to be present, and these fields are going to be dependent on each other. Electric field will depend on magnetic field will depend on the electric field. Okay, so that is how a time varying current will give rise to an electromagnetic field. Okay, so this is kind of a summary of various kinds of fields. Faraday's law. So we have seen that the electric and magnetic fields, when they are time varying, they are interdependent on each other. Now we will see the mathematical relationship. Okay, so the first one is the Faraday's law. So a time varying magnetic field induces voltage across a conductor. And if a closed circuit is available, then a current will flow. If a closed circuit is available, then the induced voltage will produce current, right? Because whenever there is voltage and a closed circuit available, then the current can flow. Now this induced EMF, this is equal to the rate of change of magnetic flux linkage minus d lambda by dt. We will discuss about the negative sign later. Now what is the flux linkage? It is nothing but n times the flux due to flux linkage of each turn. Okay, so we write this as the number of turns is constant, so you can take it out, minus n d phi by dt. So this is the Faraday's law, and this negative sign especially it is given by the Lenz's law. So what it basically states here is, see, when there is an EMF, we are not just concerned with the magnitude but the polarity as well. Okay, so what is the direction of the magnetic field, right? So that is given by the negative sign. It states that the voltage will be induced, the polarity will be in such a way that it will oppose the flux that is producing it. So the induced EMF is such that it opposes the flux that is producing it. This you can understand if you take the example of say you take a transformer core and you have the primary winding here. Okay. Now we make a current flow through this using some voltage source. Okay. Now what is going to happen? Here when the current direction is like this, what is the direction of the magnetic flux that is produced? If you use the right hand rule, then you are going to get a magnetic flux which is in the clockwise sense. Okay. Now there will be, and this is a time varying field, right? The current is time varying, so there will be a magnetic field, time varying magnetic field produced, so there will be an induced EMF. Now what is the polarity of the induced EMF? So it should be such that it opposes the flux. So the flux direction is like this. Okay. So it has, the induced EMF should give rise to a flux which is in the opposite direction. Okay. So what is going to happen? The induced EMF is going to be like this. Okay. So basically when the positive sign is here, then it will drive a current in this direction from positive to negative, right? So when the current is driven in this direction, it is opposite to the current here, right? So when this current is opposite, then the flux also, the resultant flux also, it will try to oppose it. Okay. So that is how the induced EMF will always oppose the flux that is producing it. Next we will see what is the displacement current. So in Faraday's law, what we did, we saw that a time varying magnetic field is going to induce a voltage. When there is a voltage induced, what is happening? An electric field is being produced, right? When there is a voltage. Now similarly when there is a time varying electric field, a magnetic field is going to be produced. But we know that magnetic fields, they are what? They are produced by moving charges, right? Moving charges, or you can say current. Now since a time varying electric field, this is also going to produce a magnetic field just like a current. A time varying electric field we call as displacement current. So since time varying electric fields has the same effect of producing a magnetic field like moving charges or like current, it is called as displacement current. So the displacement current density is given by dou d by dou t. This is the displacement current density. So basically displacement current is not because of flow of charges but because of time varying fields. Now the displacement current we often hear in the case of a capacitor, right? So if you take a capacitor, the current is, the charges are flowing, if this is connected to a battery source like this. Okay, this is the positive and this is the negative charge. So this is the flow of current direction. All the positive charges will be accumulated here and all the negative charges are going to be accumulated here. Okay, there is no flow of charges in between the two plates. That is why we have a dielectric here, right? So we either have a air dielectric medium or some other dielectric medium, but whatever it is, there is an insulating medium here in between these two surfaces. There is no current flowing. Okay, but even though that is the case, we see magnetic field in between these plates just like we would see outside these plates, right? So outside the plate we can use the Ampere's law, right, and we can see that there is some enclosed current, so there is a magnetic field. But what about in the case of between the plates? If you draw a Amperean path here, there is no enclosed current, but even though there is no enclosed current, there is magnetic field. Okay, so that is the displacement current. There is no conduction current flowing, but there is displacement current that is flowing. Okay, so here you can see, here conduction current flows. Okay, while displacement current is 0, there is no displacement current. But here in this ampere and path, if you are taking, the displacement current flows. Okay, that means there is a changing electric field, right? So whenever you are connecting the capacitor to a battery, what is happening? The charge that is being accumulated on the plates keep rising, and when the charge keeps rising, what will happen to the electric field? It will keep on rising, right? So here the displacement current will flow while the conduction current is 0. Why conduction current is 0? Because there is no movement of charges. Okay, so this is about the displacement current. Now when we were discussing the electrostatic and magnetostatic fields, we have seen various Maxwell's equations, right? So I will summarize here now. The first equation is del dot d bar is equal to rho v. This is in the differential form. Okay, if you are writing in the integral form, you can write as the closed surface integral d bar dot ds bar. This is going to be equal to volume integral rho v dv. This is the first Maxwell's equation. So this is also called as what? The Gauss law, right? Now the second Maxwell's equation is del dot b bar is equal to 0, or in the integral form you can write the closed surface integral of b bar dot ds bar. This is equal to 0. So all these equations we have discussed. Okay, so this is nothing but the Gauss law for magnetic fields. So this law basically states that there cannot exist a magnetic monopole. Okay, so non-existence of magnetic monopole. That means whenever there is a magnet, it will exist as both north and south poles. A single north pole cannot exist. If there is a north pole, there should be a south pole. Okay, so this is the second Maxwell's equation. Now the third Maxwell's equation is del cross E bar is equal to 0, or the closed line integral of the electric field is 0. So this is because of the conservative nature of the electric field. That means what? The work done around a closed loop is going to be 0. That is the conservative nature. Finally, the fourth Maxwell's equation is del cross H bar is equal to the current density. In the integral form, this is line integral H bar dot dl bar is equal to I enclosed, or you can write in terms of current density like this. Okay, so this is nothing but the Ampere's law. Now this is what this is. Remember, this is for static fields. Okay, static electric and magnetic fields. This is important here, because for time varying fields, these are going to slightly change. So the first two laws are same. There is not going to be any change here. Del dot d bar is equal to rho v, and in the integral form it is integral d bar dot ds bar. This is a surface integral. This is equal to the volume integral rho v dv. Okay, and the second equation is also not going to change. Del dot b bar is equal to 0, or the closed surface integral b bar dot ds bar is equal to 0. Now the third equation, we saw that del cross E bar is equal to 0, but del cross E bar in the case of time varying fields is equal to minus dou B bar by dou T. This you will understand better when you write in the integral form. The line integral E bar dot dl bar, this is equal to minus dou by dou T the surface integral B bar dot ds bar. Now if you can see, what is integral B bar dot ds bar? It is nothing but the flux, okay. And what is minus dou phi by dou t? The Faraday's law. From Faraday's law, minus dou phi by dt is nothing but the induced EMF, okay. So E bar dot dl bar is nothing but the voltage, work done, right. So the work done is equal to the rate of change of the flux. What is this? This is nothing but the Faraday's law, okay. And the fourth equation, del cross H bar, this is equal to the current density plus dou d bar by dou t, the displacement current density, okay. So this is the line integral. In the integral form, you have the line integral H bar dot dl bar is equal to the surface integral J bar plus dou d bar by dou t dot ds bar, okay. So this is nothing but the Ampere's circuital law for time varying fields, okay. So this is a more generalized form, because if you see this first and second equations are anyway same. In the third equation, if there is no time varying field, then what will happen? This term will become 0, okay. And in the fourth equation, when there is no time varying electric field, this term will become 0, and you will have the same equation like for static fields, okay. So that is why the static fields do not incorporate the time varying fields, but these four equations here that we have given for the time varying fields, this is a generalized form, okay. So this is a generalized form because it applies for time varying plus static fields, okay. So this is the final Maxwell's equations.